So now we'll get a slight reprieve from dealing with the calculations of molarity. And what we're going to look at, calculations of moles. And what we're going to look at here is a little bit some solubility aspects, particularly with respect to water. So water is an interesting molecule in that it is bent, which we hopefully remember now from multiple tests and background information and other places. And that bent shape is then further kind of explored because oxygen, being more electronegative than the hydrogen, is actually drawing the electrons towards it in each of those bonds. This means that oxygen, that oxygen has a very large partial negative charge associated with it, and the hydrogens are a very large positive charge. That differential in charge is what can help us explain a lot of water's properties, in addition to its shape being bent. But one of the big things that does is that when we now look at water as a liquid, that each of those molecules will align to minimize that charge as much as possible. So if we take a look at that topmost interaction, we have that very large partial negative from our oxygen aligning with a very large partial positive from our hydrogen. This creates a relatively strong interaction. Okay, and this is an interaction. This is not a bond. Okay, and I know that may seem contradictory because when you look at the terms, it's now referencing those as hydrogen bonds. Hydrogen bonds is a horrible term because it is referencing the interaction between hydrogens that are bonded to electronegative elements, hence the term hydrogen bonding. However, the actual interaction itself is not a bond. Okay? This is confused very often by biologists, believe it or not. So, it's not a bond, it's a very weak, or it's a very strong interaction, but you may hear people call it a weak bond. It's not a bond if you're going to look at it on that scale of interactions, which we haven't talked about yet. We talk about in the fourth unit. It ends up being kind of middling as far as strength. So why is it important? Well, that strong interaction has the ability to take a substance like salt, which is made up of sodium and chlorine. And here we can take a moment for you to think about and pause with this question. We've got two colored balls in here, one purple and one green. We're going to say one of them is sodium and one of them is chlorine, and in fact it's going to be sodium ion, and the other one will be chloride ion. Which one do you think is which? Go ahead and pause and take a minute to think about it. And hopefully you should recognize that the chloride ion should be the purple one, and the sodium ion should be, as I say and write different things. The sodium ion is purple, the chloride ion is negative. The chloride should be larger because it has gained electrons. The sodium ion should be smaller because it has lost electrons. That salt has those very large charges, and it turns out that water can align its partial charges of partial positive charged hydrogen to that chloride, and the partial negative of our oxygen, and this is going to look a little bit weird, can align with that sodium. And so what that ends up doing is that ends up ripping the sodium ions away from the chloride ions, and we have thereby broken an ionic bond. This is one of the reasons why I said earlier in the semester that the dissolving of salt is I can't focus this morning, is a chemical reaction. So what will happen is that our water molecules will coordinate positive to negative around each of these individual species, in such a way that they stabilize that charge better than if it had been left in the solid. And so what happens is we now dissolve our substances. So our ionic substances dissolve very, very, very well in water because those hydrogen bonding interactions in sum total are strong enough to pull the salt apart. Okay? So this solubility aspect is going to be very heavily dependent on the strength of the interactions between the solid, so solid-solid interactions, the liquid-liquid, and in this case, since we're really only talking about water, we can say water-water interactions, and comparing those to the strength of interaction happening between the solid and the liquid. If our solid-liquid interactions end up being stronger than the solid-solid and the water-water, sound a bit repetitive, we get the substance to dissolve. Okay? And so the big thing that you should be picking up on here, because we aren't identifying what those interactions are yet, is primarily just that compounds can dissolve in water. There are rules that allow us to predict those to a certain extent. The absolute predictions of those would be our solubility rules, which is a bit of a weird statement to make because our solubility rules are experimental results. Okay, so those are actual facts. You're memorizing somebody else's experiment. But that's what's happening with solubility. Okay, one of the other contributing factors that's interesting to look at is that temperature can also have an effect on this. Because remember, as we're going through to dissolving these things, we have to break all of the attractions between each of those particles. Okay, so we are effectively taking that solid and separating each of those pieces really far away from each other. So the process of dissolving is really a process of going from solid to gas, or even solid to liquid. Okay, so that process we've discussed and talked about before. That's the process of phase change. And to cause a phase change, we typically need heat. So when we dissolve something, it is very similar in effect as what's happening when we transition from a solid to a liquid to a gas. So if we combine those two concepts with each other, what we can get is what's known as a solubility chart. And notice that what we're going to do is we're going to plot temperature on our x-axis, and then on our y-axis, we're plotting the grams of solute dissolved in 100 milliliters of water. Because the volume of liquid can change our solubility, we want to keep that constant, which is why we're labeling that as 100 milliliters, and we're not changing that. And then what we're referencing on this axis is really just the mass of solid that we could go through and dissolve, okay, at an individual temperature. So if we were very, very high up here on this curve, we're saying we can dissolve 500 grams in 100 milliliters of water. Well, that would suggest that it dissolves a lot, so we could call this very soluble. If we looked at the other location, we're looking at, let's just go to 50, okay? We're now saying we can dissolve 50 grams in 100 milliliters. Well, that's not very much at all. That would be like saying that it was not soluble. These extra labels can help us go through and deal with interpretations if we're asked to interpret it, which you will be. Okay, and just like we did with the y-axis, we should also do it with the x. 100 degrees Celsius would be a bit silly to call, but it works. Hot. And 0 degrees Celsius, conversely, would then be cold. Now that we have these labels on here, we can try and apply that knowledge to our curve. Okay, so what is the curve referencing? Again, the curve is referencing our solubility. Okay, so what do we mean by that? That's how much can dissolve. So we're going to look at sugar because sugar is more interesting than salt at this point. So let's pick an individual point. Let's say a temperature of, let's go with a nice middle, we'll go with 50 degrees. So at 50 degrees Celsius, how much sugar will dissolve in water? So to go through and deal with that interpretation, 50 degrees Celsius, I just realized I didn't want that color on there. At 50 degrees Celsius, what we can go through and do is see where it intersects the line, and we're getting about 250 grams of sugar dissolved. Okay, that's how we are interpreting that chart. Okay, well, what if instead of having 250, because this is now saying we can dissolve 250 grams, what if I say instead I only have 150 grams? Okay, what happens with that 150 grams? Okay, well, I said at 50 degrees, my max dissolved is 250. If I only have 150 grams at that temperature, I'd be looking at a point on my curve right about here. Okay, well, what does that mean? Okay, on the curve, I could still dissolve a whole bunch more sugar. So if I have 150 grams of sugar, what I'm saying is that the solution that I created, the solution is unsaturated. Okay, that saturated solution would be the green line. Our green line, as long as we're on that line, we're generating a saturated solution. Okay, so let's change the temperature again. Let's say instead of being at 50 degrees, I jump up to 80 degrees. What would be the saturated amount of sugar that could dissolve? Well, to figure that out, we said the green line is our saturated. So I move up my red point to that 80 and 350 grams. So my saturated amount of sugar in water is going to be 350 grams of sugar. Okay? So this covers kind of two aspects or two definitions for us. It gets us the saturation line, and it also tells us what that area underneath the curve is, and that area, well, we're just going to color code that as something else, is now our unsaturated. Well, what is above the curve? Well, as you might guess, since there were three terms that we've got to identify, that above the curve is now going to be supersaturated. Okay, and what that means is we've added more sugar to water than it can physically hold. Okay, and you might be like, well, if it can't physically hold it, then that doesn't ever happen. Okay, well, here's a simple experiment for you. Okay, and since you may very well be stuck at home, you can test this and prove this for yourself. Just be careful, okay, going through and doing this if you're really going to attempt it. So what I'm going to recommend you do, and I'm going to make the assumption that this chart is roughly correct, is that what I want you to do is to go through and boil some water. Okay, so get water up to this really hot area. So hot water could burn you. Please be careful. Okay, so if we get up to that hot water, and let's make a recommendation of 100 milliliters, and what you're going to do is dissolve 500 milliliters or 500 grams of sugar in it. Okay, because you're getting some evaporation, you might get a slight variance in there. You might have to add a little bit more water to get all of that 500 grams to dissolve. But try and make sure everything is super hot and get your 500 grams of water in there. Okay, so it might be closer to 450. Okay, but dump tons of sugar in there. Okay, tons, don't do tons. You can always change these volumes or the volume of water so that you don't have to do so much sugar. Okay, at this point, what I now want you to do is to pour it into a mason jar or just a glass if you've got a glass. So you've got your glass and you've got your water inside it. Okay, and that water has a bunch of sugar particles dissolved in it. Okay, and now what you're going to do is just kind of leave it alone. Okay, if you want to get extra fancy, what you can do is get a stick that will fit over the top of your glass, tie a string to it, and hang that string into the sugar water solution. And now just leave it alone. Okay, it may take a couple days, but hopefully what will happen is that cools to room temperature. You will start to see crystals form on the string. Okay, and they'll probably also form all over the side of the glass. It's sugar, so it's okay. And what that is that the sugar that you dissolved at 500 degrees Celsius, you've now allowed this solution to cool to room temperature, roughly 20 degrees Celsius. Okay, why does that become important? Well, that solution that's now holding all of that sugar realizes that we shouldn't have that much sugar in there. And so the supersaturated solution attempts to alleviate that stress by causing that 500 to 200 gap, this 300 grams of sugar, to crystallize out of solution. Okay? And that's how we end up getting these nice kind of crystal rods that we could potentially spin around as a weapon. The sugar would crystallize and break off, so don't do that. It would make a mess. Okay, but we now have 300 grams of sugar crystallized on a string, okay, or a stick if we wanted to put it on a stick. And there we go. We've got rock candy. That whole process takes advantage of this solubility curve and that supersaturation. As long as we do things carefully and slowly, we can trick the solution into keeping things dissolved. Okay? So, I'm going to delete all that. And we've got our solubility curve that shows sugar and salt. Well, a lot of substances will dissolve in water. And so not all solubility curves will look the same. Okay, but you will notice a general trend in the vast majority of these. They all increase upwards. Each of these substances will increase in solubility as we add temperature, which makes sense because what did temperature do? It caused the crystal to break apart. So adding heat and water should just speed that breaking process. You'll notice that's not 100% perfect. There are some weird exceptions, like in this case, our selenium, what is that, selenium 3 sulfate? That's not selenium. Cerium? I think that's cerium. 3 sulfate does not increase in solubility, it actually decreases. So that's just kind of an interesting observation. It's not a perfect system, but we're looking at those same general principles that we talked about applying to this. So, why look at these solutions? Well, as you might be able to predict by looking at some of these, we may have seen these terms before, like potassium dichromate. Okay, potassium dichromate or even lead nitrate are things that have shown up in our labs. We've had those substances and we allowed them to react with other substances. Okay, but those reactions, when we took those substances, weren't in the solid phase. They were in solutions. Well, those solutions now change concentration. And depending on our concentrations, we could get weird results based off of the solubility curves. So we need to be able to understand how much compound is actually dissolved in those solutions. And that's where this is going to become extra fun for you. And that was sarcastic because we're now looking at more conversions. So I've got this chemical reaction. You should be able to tell me what kind of chemical reaction occurred. So yes, you should take a second to think about it. We've got that pause button. Okay, this chemical reaction is a double replacement. Okay, how do we know that? Well, what we're trying to do is identify the pieces that we see within it. We've got metals and we have non-metals. So that's already starting to fall into that pattern. If we look at our products, the products also show that same pattern. Okay, so for sure we're looking at a double replacement. Okay, so now I want to push this further and say, well, how am I going to quantify this? So in a quantification, I'm going to have to run a measurement. Okay, and in this case, I'm asking an easier question. Let's take a look at our silver bromide. So the silver bromide, we've got, in theory, a multiple choice question here. Which ones are silver bromide? AgBr. I want to be able to quantify that. Okay, so if I was to measure the silver bromide, what device would I use to measure? Okay, and so what that question is asking, mass, volume, time, and length, right? Those were our core measurement systems. If we had mass, we could then do a balance. If we had volume, we could do a graduated cylinder, which is way too many letters, but oh my goodness. And of course, too many letters means I'll spell it wrong. Time, we could use a clock, and length, we could use a ruler. Okay, well, when do we use each of those things? Well, a balance is useful for when measuring solids. Okay, it can still measure other things, but the solids tends to be the easiest. Volume is great for liquids. Okay, a clock is time, so we're not really measuring solids, liquids, or gases. And a ruler is measuring the length or size of something. So again, that doesn't make sense for our individual phases either. Okay, so those don't work to measure our phases. They would measure changes in our phases, okay, be it their size or them appearing or disappearing. Okay, so if we go back and use that information with our equation, okay, the silver bromide, I'm going to throw gases in there under volume. They're usually easier to measure in volume. Silver bromide is which phase? Well, as we've discussed, that parenthetical with the solid, or the S, means solid, which means the best thing to use to measure this would be a balance. Okay, so nice and straightforward. We can use a balance to weigh that out, and we now know how much silver bromide we produced. Okay, so then the next question, where did it come from? Well, this is hopefully an easy question. This is why we have a chemical reaction. That silver bromide came when I mixed these two things together. Okay, when I mixed the aluminum bromide and the silver nitrate together, that then produced a reaction where silver bromide formed. And that's how I could then weigh the silver bromide. Well, if we're looking at this from the chemist's point of view, let's say silver bromide is an exceptionally useful thing. Okay, I want to know how much I can make before I start making it. Because if I start making it and it makes thousands of tons of silver bromide, well, that's probably something I don't want to make in my house because it could kill me in the house. Okay, but if it only makes gram amounts, maybe that's something that's easy for me to do inside my house and I don't need a lab. Okay, so the scale of these things becomes important. So I want to know, theoretically, if I start with X and Y amounts, and we'll address the amounts here in a second, of the aluminum bromide, how much silver bromide could I make? Okay, so you should already be thinking, well, dang, that's going to require a conversion. And yes, it will. So this is where we're going to bring back our conversion aspects. But it's going to become a little bit trickier. And the reason it's going to become trickier is that when we look at those conversions, the chemical equation allows me to relate silver bromide moles to moles of aluminum bromide. Okay, and in this case that would be 3 and 1. So the equation sets me up with these moles. But as we just addressed, if I'm going to measure this, I need a balance. I would be needing grams. So I'm going to have to do a mole to gram conversion, okay, as we discussed in our past videos. Okay, but now we bring in the next thing. How am I going to measure the aluminum bromide? Well, the aluminum bromide has this aqueous thing next to it. So if I went through to measure out on a balance to get a mass so that I could also do a mole to gram relationship, I'm going to run into an issue. The mass that I'm now obtaining is not of aluminum bromide. Okay, and you might be a little, but it's still aluminum. It is, but it's aqueous. Aqueous meant dissolved in water. If it's dissolved in water, we now have a problem. Because when I go through to take that balance or take that weight, the mass that I'm going to get is both water and aluminum bromide. Water isn't doing any chemistry here. It's not showing up in my conversion factor coming from the chemical equation. Okay? The only thing that I need access to is the aluminum bromide. But if it's already dissolved in water, how do I pull that information out? Well, I'd have to be given more information about it. The information that I would need would be a concentration of the solution. Okay. Well, what is concentration? Okay, depending on your age, you may have heard reference to something like ABV. Okay, ABV is alcohol by volume. Okay, that is a concentration. Okay, you could have seen other things. Our concentration is really just relating the amount, okay, of one substance to the volume of our solvent. Okay, and that should be a nice big tip-off here that we're generating a conversion factor. We've got an amount over a volume. We're looking at 2 units and their relationship. And that's exactly what we're going to do here. Okay, so we're now addressing concentrations and what units we should be using for concentration. Okay, so let's think about this as far as a chemist would go. Okay, what unit do I want to use? Because as we already see here, we've got one. We could use alcohol by volume. Okay, we could use the mass per volume of the solvent. Okay, that one becomes tricky because that starts to look an awful lot like density, right? And we don't want density here. We're talking about the mass of a solute dissolved in the solution. So mass per volume actually may be a horrible idea because that could easily be confused with that formula that you were told to not memorize for the record for density. Okay, so we don't want mass per volume. We for sure need some kind of volume measurement because we're looking at water and water was a liquid. And then we need some kind of amount measurement. Okay, and we just said that mass was a bad idea. So what other amount measurements do we have? We have a counting measurement. We have that counting measurement of moles. Okay, why is that going to be a useful one to measure? We'll go back up to our chemical equation and look at the stuff we've already addressed. Okay, we've got moles per gram. We've got moles per mole. Okay, moles shows up again and again and again when we're dealing with our chemical equations. So if I'm going to look at a concentration as a chemist, it probably makes sense that the concentration I want to show is the relationship between the moles of my solute and the volume of my liquid. Okay? And that is indeed what we ended up picking, which we'll see here in just a second with a deletion of everything. So if you want to write it down, now's the time to do so. And we end up with a new concept, so don't stress about the words yet. Okay, and we have a concentration, and that concentration is defined as moles of a substance per liter of solution. That substance can be a solid, liquid, gas. Okay? So moles of any substance dissolved in a solution. It is most commonly water when we're talking about Gen Chem because we want to minimize your toxic exposures. Okay? But it could be any real liquid. Okay? I now have a concentration. If I use the term concentration, that could easily be confused with, like we said, ABV. Okay? And I don't want it to be confused with that, so I want to be a little bit more specific in my concentration reference, and that's where I define that this relationship between moles and liters of a solution is known as molarity, okay, shown as a capital M. Just to add a little insult to injury, we're not going to use this, so don't worry about writing this down. If you move into 151, you'll see it there. We could also have referenced it as a mass of substance per liter of our solution. Note that the mass we're using as a unit is kilograms. Why kilograms? Because that gets us out of the gram measurement, which could get us confused with density. Okay, this is also just as equal a concentration. We would use it in slightly different situations. This unit or measurement or concentration, conversion is known as molality. Okay, for those of you being like, that sounds awfully similar to molarity, it was intentionally picked so that people would recognize that they were equally valuable. That's just dumb, but that's why we picked molality as a term. Molality tends to show up in a lot more places. For instance, if you've ever lived in cold environments, salt concentrations for de-icing roads are typically referenced in molalities because you're looking at someone monitoring the concentration of salt on the road, and that's easiest to measure in kilograms. They aren't doing a conversion of a substance, they're just trying to get rid of ice. Okay, and because their use is different, they change the concentration unit that they're referencing. Okay, so it is very system dependent, if you will. So we now have this new concept of molarity. The next thing you might be going as an aha moment, in fact, I'm fairly certain a few of you might be doing this, is that if we looked at our bottles that we've been using in lab, because a couple people asked me about it in lab, they're like, why does it say 0.1 M? What is that M? Guess what that M is? It's the molarity. That molarity is now referencing the concentration of that substance that was in that solution. So, for instance, that was very commonly found associated with 0.1 M AgNO3. Okay? What we were saying by saying that is there are 0.1 moles of silver nitrate in 1 liter of that solution. Okay? That's what it meant. Okay? Which is going to get to an interesting statement. When we write it out on the bottle, we just wrote 0.1 capital M AgNO3. Okay, why did we not write out moles per liter? Well, moles per liter takes more effort. It also shows a fraction, both of which are challenging things for people to deal with, and so we emotionally have stepped back from showing that, and we simplify it out so that we only see the M, okay, that capital M. Okay, while we may be able to do that as chemists that have learned and understood the meaning behind these terms, because we understand this equality very, very, very well, okay, you, on the other hand, are still learning, which means when you see capital M, write it as the moles per liter. Okay, that should be your immediate first step. If you don't do that, you will have trouble doing your conversions later on. Okay, so please use that advice to ensure that you can do your conversions. Speaking of which, we've got some conversions. So, what is the molarity of a solution containing 24.0 grams of sodium hydroxide in 1.1 liters of solution? Okay, so again, what are we aiming for? Being asked to solve for molarity, which would be capital M, which we just said, oh my God, don't write capital M, write moles over liters. Moles of what? Okay, well, in this case, we're dissolving sodium hydroxide, so we'll say moles of sodium hydroxide over liters of what? The liters of our solution. Okay, so if that's what I want for a final answer, I now need to come up with a way to organize all of the given information so that I can figure out what numbers need to go in front of this. Okay, so let's go back and look at the rest of the given information. I have 24.0 grams of sodium hydroxide, and I have 0.1 liters of solution. Okay, so let's see how far you can get. So again, I'm going to recommend a pause here. We've got all our basic pieces put out there. Let's see what you can come up with. Yep, please do it. That would be the space bar. Okay, so now how do we go through and set this up? So we need to introduce some of that given information. My argument would probably be to introduce the liters of solution. In my answer, that liters of solution needs to show up in the denominator, so I'm going to put liters of solution in the denominator. Since I know a number with that, it's 0.100 liters. Really all we're saying is I want to place that given piece of information in the denominator. So since this is a single piece of given information, I'm going to put a 1 there. This is one piece. Okay, I don't want to put anything in the numerator because now I'm adding another piece of information. So one piece, and this was given. Okay, so that's cool. That starts to set me up on the correct path. The next thing is I want moles of sodium hydroxide in the numerator, right? So I can go back and look at my given information and be like, well, do I have that? No, I don't. Okay, but as a potential, I do have the grams of sodium hydroxide. So I do have that substance showing up. Okay, so I could place the grams of sodium hydroxide in the numerator because it's the substance, and the substance needs to show up in the numerator in my answer. So I'll go through and do 24.0 grams of sodium hydroxide. Again, this is a single piece of information, so I don't want to put it in any kind of fractions with anything else. We're just going to put a 1. Okay, and this was, again, given. So if we went through and solved this, we'd have grams per liter. I want moles per liter, so that means for sure I need another conversion. In that conversion, I need moles of sodium hydroxide. Okay, I also know that I do not want grams of sodium hydroxide. So I could place the grams of sodium hydroxide in the denominator such that it would cancel. So now I have a conversion factor that I would need to recognize that I need to have. So does this thing exist? Do I have a relationship between moles and mass? If I do, where is it found? It does exist. It's found on the periodic table. Sodium has a mass of 23, ballpark. Oxygen has a mass of 16. Hydrogen has a mass of 1. I could now add all of that up, and I would get 40, okay, grams per mole. I could now insert the numbers into this. This is 40 grams, and that is 1 mole. When I now go through and look at the unit work, it's all established and aligned such that I could go through and now enter this into a calculator, and hopefully what we would get after we did all of that would be 6. Okay, so your calculator should spit out the number 6. And we could call this 6 moles of sodium hydroxide per liter, or we could write it as 6 capital M. Okay? Just to be extra irritating, because that's just the way life rolls, we should evaluate sig figs. When we look at our given information, we're supposed to be reporting to 3 sig figs, so 6 molar is technically wrong, and it should be written as 6.00 capital M molar sodium hydroxide. Okay? So hopefully that makes sense, which means you should now be able to go through and solve this next one. Okay? Again, I'm going to recommend the pause, and what I'm going to tell you right now is I'm going to pause the video and actually draw in all of the work, so you're not going to get a big talk through on this. So please spend some time to actually try and get it figured out on your own first. Pause the video. So here's a bunch of stuff that I would have gone through and done to highlight where I'm going and establishing it. And then again, we should be able to work forward from this. Ta-da! So there's all of the work. Note, we've identified where that information is coming from and how we got it. Notice that the placement of each of those things has to do starting from that very first piece of given information on the right-hand side. Remember, we worked right to left, not left to right. Okay, so the moles, the K2Cr2O7 was placed in the numerator because our substance is in the numerator. Okay, and that establishes this conversion and it allows us to work with it. We've now done 2 different kind of conversions with molarity. You're now responsible for digging into it and trying to figure them all out and start getting that practice. You need that practice, okay? Largely because you need the practice with the actual conversion process, and now you also need the practice recognizing where to find that information and how to pull it in and get that detail. Okay. Where this is ultimately going to go is into a much more difficult situation. Okay, and so don't worry about this Teams of thing at the bottom here, and we'll get rid of that internet meme. But we've got a big text box here, so go ahead and spend the time to go through and read it. I'll actually let the video run while you read this. So in theory, hopefully my typing and underlining was not overwhelming. I went through and underlined bits of information that I pulled out as being useful for going through and solving this. So we have 2 bits of information about our acid, and we have 2 bits of information about the barium hydroxide. Okay. Interestingly enough there, you're seeing some extra information being given to you as I write this down. Okay. One of the critical pieces to note is that we have to know what these substances are. So to even attempt to solve this question, you have to have nomenclature handy. So it is a much more advanced and challenging question because what I'm asking you to do is think about those pieces. Okay? When it comes to an exam, I would not ask this level of difficulty of question because of the sheer volume of things that you need to be able to process to go through and do it. So when you get it wrong, I have no idea why you got it wrong. It could have been the English language. It could have been that you didn't deal with molarity right. It could have been you didn't understand volumes. There's so many different places that this particular question could go wrong that it's a very difficult question to ask on an exam. Okay? The last bit of information that you would need to go through and solve this question is the relationship between barium hydroxide and nitric acid. We said that this was that we're in a chemistry class, which means a chemical reaction makes a heck of a lot of sense to be looking at. So if you're seeing a question that lists multiple substances, writing down a chemical equation, if it hasn't been provided to you, is an excellent first step. When we write down those two pieces, we then have to be able to decide what kind of chemical reaction is this. Okay? Hopefully what you recognize is this is an acid-base reaction, and we're looking at doing a neutralization of the acid with the base, which means we're going to produce water and a salt, which is effectively a double replacement. Okay? Once we've predicted our products, we also need to ensure that we've predicted the products correctly. Barium is a +2, nitrate's a -1. We did not do it correctly. Now we put the 2 in, and now we've got a proper equation. Once we have the proper equation, we can now go to balance the entire equation, and we should note that we will need to add a 2 in front of the nitric acid and a 2 in front of the water, and we now have a balanced equation. You now have all of the given information. All of this information was stashed within that sentence or sequence of sentences, that paragraph. You are responsible for needling all of that out and coming up with an interpretation for it. Okay? Now you have to go through and organize this material in such a way that you can go through and solve. That organization process should be through dimensional analysis. If you want to do it in another fashion, that is entirely your prerogative. Okay? All I'm telling you is that other fashion will very likely result in you getting the question wrong. Not because I'm being mean, but because you're going to lose track of where those pieces are. Okay? And this question is kind of neat, and I thought I had listed out all the individual steps that you would need to go through to answer this. So we're going to advance through some kind of nonsense stuff you don't need to worry about. Okay, so this is that nonsense. And apparently I did not summarize everything for you on this. Okay, so I apologize for that. I will try and organize a slide because there's a similar example later in the slideshow or in the unit that explains all of the individual pieces that you would have to go through and solve a question like this. Okay, so with that, I'm going to go ahead and stop this video because as you saw as I advanced the slides, the very next topic we're moving into is now gases.